Hi there, and thank you, as always, for clicking on this lesson. In this lesson, we are going to look at the properties of logs. Please give this video a quick thumbs up if you find it helpful. Subscribe to the channel so you don't miss any math help. Drop a comment to engage or ask me a question. And please do not forget to check out the practice set for this concept. Very, very important, particularly with this concept more than with some others. Now, before we dive in, there are a few key ideas I want you to remember as we derive the properties of logs. I wanted to go over these because I am going to go through some steps, and if certain things are not fresh in your memory, like I might lose you on a couple of steps, we definitely don't want that to happen. So first is what is sometimes called the golden rule of algebra. Whatever we do to one side of an equation, we must do to the other. So in these derivations, I'm going to do some stuff that you might be wondering, why would you do that? Well, the why is because it's going to get me where I want to go. What's important to remember is that I can do anything I want to an equation as long as I do the same thing to both sides. So we want to preserve that equal sign. The left is equal to the right, so I can do whatever I want, okay, to the left side. As long as I do the same thing to the right side, it will still be equal. The next two are some laws of exponents that have been covered. The first one is when you multiply like bases, you add exponents. So for example, if I have x squared times x cubed, that's x times x. This is x times x times x. And all together we have 1, 2, 3, 4, 5 x's. So it's x to the fifth. And so that is really x to the 2 plus 3. Now, in this particular lesson, we're going to be using that in the other direction. So we're going to have things that are added together, and we're going to split it up. So we're going to be starting like that and rewriting it like we have it on the left there. That should be fine, just like that's the property we're going to use. In a different derivation, we're going to use this one. So this would be when you're dividing like bases, you subtract the exponents. That's something like this. If you have x to the fifth divided by x squared, you can cancel out some of your x's there. Okay, so it cancels out and you are left with x to the third, which of course is 5 minus 2. Okay, and as with the previous one, we're actually going to be applying it in that direction. Okay, so we wanted to bring those to the forefront of your mind. And we also want to remember what logs do. And so this goes back to a previous lesson, which I will link up here if you'd like to go check that out, where we introduce what a log is. And so in this case, we have a base of a. And if I wanted to get the value of that exponent, I could get that by taking the log base a, and we would actually say it that way, log base a, and that undoes the base of the exponential. So we're approaching it like an operator. So log base a of a is whatever the exponent is. Okay, so we want to keep that in mind. You can tell we're going to be doing some stuff with some logs here. Okay, so without further ado, let's get going. So the first property is this. If you have log base a of x plus log base a of y, we want to know what is that equal to. Now, you might think, okay, you might think, well, would that be log base a of x plus y? Okay, so you might hypothesize this. So if you had log base a of 2 plus log base a of 3, well, shouldn't that be log base a of 5? Okay, we'll put a bunch of question marks around there. Well, that is what we want to find out. So for the purposes of this derivation, instead of working with a question mark, and if you could see my notes here where I was kind of outlining what the lesson was, I actually did this with a question mark and then thought, well, that's a little clunky. So why don't we just call it n? Okay, so log base a of x plus log base a of y, that's n. And what I want to know is, what does n equal? Well, first thing I'm going to do is I am going to raise each side with a base of a. So here's essentially what I'm going to do. I'm going to take the left side and make that the exponent. Okay, it's kind of a messy exponent. And I'm going to take the right side and make that an exponent. And because that's a log base a, I'm going to raise it with a base of a. Okay, so essentially what I did was I took the left side of that equation and I said, I'm going to make that the exponent. Now, if it's true that that is equal to n, then that must be also equal to a to the n. So as long, again, this goes to that first thing. You're probably wondering, why would you do this? Because I can, and because it's going to get me where I want to go. Okay, so what we're doing is just applying some stuff that we know. Okay, so we raise both sides with a base of a. Now we're going to apply the second thing, and that is this. If you have something like that, okay, so you've got something and you're adding the exponents together, that came from multiplying like bases. And so instead of an x and a y here, I actually have log base a of x and log base a of y. But here's what it would look like. A to the log, that's an O, log base a of x times a to the log base a of y. And that's equal to a to the n. So again, that was that property, but it was kind of going in the other direction. Now we want to remember what logarithms do. So on the previous slide, I reviewed it in this direction where you have, I don't know why I keep wanting to make that an a, log base a of a to the x is equal to x, but this is also true. A to the log base a of x is equal to x. It's the same property, just kind of worked a different way around. And so the base of a and the in the exponent and the base of a in the logarithm undo each other, leaving me with just an x. So this becomes an x and this becomes a y. And they are being multiplied together to give me like a to the n. So x times y equals a to the n. You know what I'm going to do? I'm just going to rewrite that real quick. It's just xy. Okay, we don't need to do x times y. All right, now this is not where I really want to be because remember what we were looking for was the n. Like what I'm really interested in is n. N is now stuck in an exponent. Well, it is super handy then that we have a tool for getting stuff out of an exponent, and that is to take the log of both sides. So if I take the log base a of a to the n, I must take the log base a of the xy, and right here, on this side, okay, again, it's this property here, log base a of a to the n is going to bring me back to n, and n is equal to log base a of xy. Therefore, what do I know? I know that log base a of x plus log base a of y. Now that was equal to n, but now I know what n is. N is log base a of xy. Okay, so if you're taking some notes, okay, if that's how you're approaching this, that you want to write down. Highly unlikely that anybody is going to ask you to rederive the property, but knowing the property, yes. Now you can see this in other forms. It's the same property, except that you might see like a base x with like an m or an n, or like you could see other letters. I'm using a base a with like x's and y's as the argument of the log, but You could see other notation there. You will sometimes see this in parentheses. With the multiplication, it is usually implied that you're going to multiply and then take the log. If it's adding, it is not assumed, and so you would need the parentheses. So sometimes you'll see the parentheses there. Like when it comes to typing it, it's usually very clunky, especially if the thing is a fraction. So we don't always type it, but you could see that. So what does that tell us about our example problem up here? Well, it tells us that log base A of 2 plus log base A of 3 would be log base A of 2 times 3, or 6. Now, if you do not believe me, if you're like, wait a minute, internet lady, you might not know what you're talking about. Go grab a calculator, okay? And you don't have to deal with the base on there. You could just do log 2 plus log 3, okay? And get a decimal. For that, it'll be some kind of like crazy decimal. And then do log 6. And what you will find is that it is the same decimal, okay? So if you don't trust the internet lady, you can go grab a calculator and verify it. All right, so that is our first property. Second property, this one involves subtraction, and I've got it set up here the same way, where like what we want to know is what is happening if we subtract the logs. And so we're just going to call that n, and we're pretty much going to do the same thing. So we'll go through this one a little bit faster. So we'll have log a to the log base a of x minus log base a of y equals a to the nth power. Now, this time we're going to use the other property, which is if you have two like bases being divided, you would subtract the exponent. So this time, this will combine to a to the log base a of x over a to the log base a of y. And once again, a to the log base a, those are undoing each other, and we end up with x over y. Okay, so we're just undoing it. Now I have the same problem I had before, is the thing I was looking for was the n up here. Okay, it was the n, and the n is stuck in the exponent. So we're going to go ahead and use log base a to undo that. And if I log base a one side, I've got to come over here and log base a the other side. Right here, log base a of a to the n is equal to n. And here is my expression. So now I know what n is equal to. Therefore, property 2, if you have log base a of x minus log base a of y, that is not actually equal to log base a of x minus y. You're actually going to be dividing them. And that is property 2. Again, not likely that somebody will ask you to rederive it. And there are other ways of deriving it. So it could be that you have a teacher, your teacher's done it a different way. You could probably throw this into ChatGPT or something, and it could show you another way to do it. I'm not going to claim a monopoly on that. Bottom line, though, is that when you collapse your logs, they collapse to division. What is a key idea here is that because logarithms and exponentials are related to each other, we've already established that in some earlier lessons, that they are inverse operations and they undo each other. It makes sense that their properties are also going to be related. And the way we're coming up with the property is we're essentially taking the logarithm, converting it over to an exponent using the property of exponents. Okay, that property there, to rewrite it and then putting it back into logs. So essentially what we're doing is we're starting with something in logs, changing them over to exponents, using the properties of exponents, because we already have those, and then turning it back into logs again with the logarithm property, like now as like a new tool in our toolbox, something we can use. Now, there is a third property. Now, the derivation of the third property, we are going to do this one differently. So to derive this one, we will use inductive reasoning, but not establish a formal proof. So what I was just doing was more deductive, where I was starting with like a statement and then using known facts, like things that we had already established, like our properties of exponents or our knowledge of what logarithms do, and using that like known facts to get to where we needed to go. Inductive reasoning is different. Okay, this means we will show that it is true for the first few cases and use that to argue that it will be true for every subsequent case. So that is essentially how inductive proofs work. You show that it is true for the first, usually 2 cases. Sometimes you have to go a little bit more than that. It depends on what you're trying to prove. And then you will generalize it with variables. So you'll say if it is true for one case, then it must be true for the next case, or like n+1. Okay, we're not going to go through that. There is a way to do this such that it's proved beyond any doubt, but in this lesson, we will simply argue that it is a reasonable conclusion based on what we can see. So we're going to use inductive reasoning, but we're not going to go into like an inductive proof. Typically, that is not done at the Algebra 2 pre-calculus level. You might see something like that in a calculus class, but it would come beyond that. Okay, so here are the first cases that we're going to look at. We're going to look at log base a of x squared, and then we're going to look at log base a of x to the third. And after we do that, we will then be able to make the argument that this would work for a 4, a 5, a 6, and by extension, but maybe not as obvious an extension, it would also work for things like 1/2 or negative exponents as well. That gets tricky, but won't be unreasonable. So looking at this, we've got log base a of x squared. So I'm going to say, let's look at what x squared is. X squared is x times x. And we'll just do these side by side. I was going to do them separately, but okay. X to the third is x times x times x. And then using what we just learned. So we just learned that log base a of x times log base a of y is equal to log base a of xy. Now, come up here, okay, if you look at the upper right where I was writing, instead of having a y, let's just say that it's the same number twice. Okay, like it could be different numbers, but like hypothetically, let's just say it was the same number. So instead of x times some different number, y, okay, it's x times the same number. Well, now when I write it like that, log base a of x times x is log base a of x plus log base a of x, which means that I have 2 log base a's of x. In other words, log base a of x squared is equal to 2 log base a of x. Coming over here to the 3's, okay, I'm actually going to use what I just did. So we could think of that as log base a of x squared times x, okay? So that would be, now I can use what I got up here, okay? X squared, like so. Okay, if you didn't see, I was just writing right up there, if you can see where my pen is. Okay, so that means this would be log base a of x squared plus log base a of x. But what did we just show? We just showed that log base a of x squared was equal to 2 log base a of x. So log base a of x plus 2 log base a of x is 3 log base a of x. Therefore, log base a of x cubed is equal to 3 log base a of x. Imagine that. Interesting. Okay, so what can we conclude from that? We are going to now argue it's reasonable then that log base a of x to any power, okay, because if this worked for 2 and it worked for 3, this is not a stretch that it's also going to work for 4 or for 5 or for 6, or like you could just keep going with that. It would be equal to y times log base a of x. In other words, the exponent can move down and become the coefficient, and vice versa. You could have a coefficient and you can bump it up into the exponent. Now, it does take more nuance to go through. Okay, well, would this work if you had a 1/2? Would it work if the exponent was negative? That again gets a little bit more like nuanced, and we'd have to really do more of a deep dive. I think that this though establishes that this is reasonable. It probably does work for those other numbers, even if we're not going to take the time right now to show that it does. Okay. So what can we do with these properties? And just as a recap, here are what the properties are. Log base a of x plus log base a of y is equal to log base a of xy. Log base a of x minus log base a of y is equal to log base a of x divided by y. And log base a, sorry, I triggered something on the pen that I was writing, of x to the y is equal to y log base a of x. Those are the 3 properties that we have. Now, these properties give us the flexibility to rewrite expressions in other forms. Sometimes this is just called equivalent forms. So you can take a log expression written one way and write it in another way. We can use them in either order. So we can start with something that looks like the left and rewrite it as something that looks like the right, or take something that looks like the right side and rewrite it so that it looks like something written on the left. That leads us to the 2 kinds of problems. We can expand and collapse, and you'll notice that I put those in quotation marks. That is a very broad and unspecific way of expressing it. By expand, what we mean is write each expression as the sum or difference of logs of a single term. That just gets very clunky, and teachers don't want to say that all the time. And so we just do a ton of examples and hope that students figure out what we mean by that. By collapse, we mean write each expression as a single logarithm with no coefficient. In other words, kind of like collapse everything together. These are often doable in one step, that is with no work, but they do take practice. So many of these, I won't go and say like every single one that you could ever find on planet Earth, I could do it in one step, but most of the high school level ones, absolutely, your teachers can do these in one step. They do not have to show any work, but it does take some practice to get there. So do not skip the practice set for this. Please click on it at the end of the video, and any other problems your teacher may give you to work on, because being able to do these in one step is absolutely something that you would like to be able to do. We would like these to be no work kinds of problems. So let's look at a couple examples. This is an example of expand. So this would be write each logarithm as the sum or difference of logarithms of a single argument. Now, I'm just going to demonstrate like I can do this in one step. This is going to end up being 2 log base 3 of x plus 3 log base 3 of y minus log base 3 of z. I can do it just like that. Don't have to show any work. And now that you can see the expansion, you might see where some of this is coming from. Now, typically when you start doing these though, you need to do some steps until you can get your feet under you and get your brain thinking through all of the different steps. So typically in a problem like this, we would start off dealing with the division and we would apply this principle right here, which says that the quotient of the two that came from subtraction. So I just wrote it up there in the upper right for you. And so the first step to this might look something like this, where you expand that out by subtracting. Now, the log base 3 of z is technically done. We're just going to bring that with us every step along the way, and we're going to shift our focus over to what had been in the numerator, and that is our x squared times y to the third. Well, that's useful. We've got this property that says that if you have two of them multiplied together, that came from adding them. And so this could be expanded as log base 3 of x squared plus log base 3 of y cubed. And then that log base 3 of z is along for the ride. And now we apply the last property, which told us that if we had x raised to an exponent, that exponent could come down front. And so the 2 is going to come down in front of this log. And the 3 comes down in front of this log. And there's the answer that I got in one step. Now, if you try to do these out of order, okay, so if you try to bring down the exponents of the 2 and the 3 before you actually split them up, you will run into some kind of problem where you've got the 2 and the 3 trying to come down in front of the same logarithm, and then you end up inadvertently applying the 2 and the 3 to both the x and the y, when really the exponent of 2 is attached to the x and the exponent of 3 is attached to the y, and we don't want to like mix that up. You want to keep everything separate. So if you try to do these out of order, they often will self-check for you. Because you'll slam into something that you don't know what to do with. With these, do make sure that there is some way to differentiate between your 2's and your z's. My 2's, I tell my students this all the time, my 2's will bounce back and forth between something that is loopy-looped and something that's not looped. There's no rhyme or reason to that, but my z's are always crossed. Always crossed. So you can always loop your 2's if that's what you want to do, but do make sure that you're not going to confuse your 2's with your z's, that there is some kind of continuity in that. All right. Now this one is a collapse. So we're going to try to take all of this and write it as a single logarithm. Now, I don't think I've mentioned this at this point in my series of lessons, so you may or may not know this depending on where you're hopping in. But if you don't see a base on a logarithm, the assumed base is 10. Okay, and the name for that is called a common log. And you will find that on every scientific calculator. You will find it on every single scientific calculator. It's called a common log. You do not have to write the base of 10. I know for me, sometimes I start doing base 10 logs because I get tired of typing the exponent all the time. Okay. So what we're going to do is move all these coefficients into the exponents. And there's actually multiple ways you can do this, but we will try not to complicate things. So that's going to give us log x to the third minus log y to the fourth minus log z to the 1/2. Now here, I can do this in one step here. I am going to work through the logistics of it. And then if you hang with me, I will tell you how you can avoid having to do this. So looking at the first two, if I'm subtracting, so I'm just going to focus on this part right here. This would be, we're going to use this property here. log x minus log y is equal to log of x divided by y. So in this case, instead of x divided by y, it's x to the third divided by y to the fourth. And then we're subtracting log z to the 1/2. Now, to keep going with that, we end up here. So we end up with x to the third, over y to the fourth over z to the 1/2, at which point most of my students are completely checked out, thinking that is ugly. I don't want to deal with that. Well, there's good news. One is if the directions say to write it as a single logarithm, you've technically done that. That is down to a single log. The fact that the argument looks like a disaster has nothing to do with whether or not you satisfied with the directions we're asking you to do. You did. But we would like to be able to write that cleaner. Okay. And so let's take a look at how that would work. I'm going to go through this one time. X to the third over y to the fourth over z to the 1/2. That fraction bar, we're going to take that and write that as division. So x to the third over y to the fourth divided by z to the 1/2. Now, if you've followed my videos from the beginning, which if you're jumping in at Algebra 2, you might not have done that, but there are videos back there where I go through like what division is. Division means to multiply by the reciprocal. And just as an illustration, I'm going to come over here to the left. If you have 4 divided by 2, that is the same as 4 times 1/2, or 1/2 of 4. 4 divided into 2 groups means you have 2 in each group. Half of 4 is 2. Okay, so dividing by number is the same as multiplying by the reciprocal. So moving back over here to the right, that is the same as 1 over z to the 1/2. And that we can just multiply straight across. So this messy looking thing here could be written as x to the third over y to the fourth z to the 1/2. Or you could do this, x to the third over y to the fourth square root z. That might open up another can of worms because now we have a square root in a denominator. Yeah, I'll kind of put a big question mark there. Okay, but a little reminder that an exponent of 1/2 is the same as a square root. Now, here's the shortcut that you were probably hoping for. Anything you see that is subtracted is going to land in the denominator. Okay, so when you see that the 4 log y is being subtracted, or the 1/2 log z is being subtracted, that is going to plant that in the denominator. If you're interested, here is one other way you could think about that. Okay. In this very first step, you could do log x to the third, and instead of moving the 4, move it as a -4. And instead of as a 1/2, move it as a -1/2. So that would give you plus log y to the -4 plus log z to the -1/2. Now, when you are adding all those exponents together, or arguments up, all the logarithms together, you would get log x to the third, y to the -4th, z to the -1/2. And now you can go and use your laws of exponents, where you know that a negative exponent will dump something into the denominator. Okay, and you'll notice that got us to the same spot. So I always like to show my students multiple ways of doing things, that there's always multiple ways, and we want to be creative and use the things that we know. Okay, So please do not forget to give this lesson a like if you found it helpful. Subscribe to the channel for more math help. Leave me a comment or a question. Is there something that was interesting? Is there something I did that was confusing? You want some clarification? Please engage and check out the practice set for this lesson. I am going to link that below, and I hope to see you in a future video.